Welcome to DAR Tutors. Today, we're covering hypothesis testing. Our objective in this video is to explore hypothesis testing for two key areas within the IBAI-HL curriculum. First, we'll examine tests for a population proportion, where we use the binomial distribution as our model. Second, we'll cover tests for a population correlation coefficient using a t-distribution. For both of these topics, you will learn to first, state the null and alternative hypotheses. Second, apply either the p-value method or the critical region method to make a decision. And third, interpret your findings in the context of the problem. This means translating the statistical conclusion back into a meaningful statement about the real world. We begin with hypothesis tests for a population proportion. Our goal is to determine if the true proportion p of a population having a certain property is equal to a specific value p0. Imagine you're trying to find the proportion of left-handed people in a country, or the proportion of biased coins. This is the type of question we're addressing. We formulate our null hypothesis as H0, p equals p0. This represents the status quo or the assumption of no effect. In our coin example, this would be H0, p equals 5, meaning the coin is fair. The alternative hypothesis, H1, is what we are trying to find evidence for. It challenges the null hypothesis. The alternative can be one of three types. It can be H1, p0 for a one-tailed test where we are looking for evidence that the proportion is larger, or H1, p0 for a one-tailed test where we are looking for evidence that the proportion is smaller. Alternatively, it can be H1, p is not equal to p0 for a two-tailed test where we are interested in any difference from the null hypothesis, regardless of direction. To test these hypotheses, we take a random sample of size and from the population. We then count the number of members in the sample that possess the property of interest. Let's call this number x. This x is our test statistic. The number of successes in n trials is exactly what the binomial distribution describes. So, under the null hypothesis, our test statistic follows a binomial distribution with parameters n and p0. We write this as x is distributed as BEN PQ. This is known as the null distribution. Now let's see this in action. Our first worked example involves a coin toss. Teresa flips a coin 20 times and gets 15 heads. She suspects the coin is biased towards heads. We need to conduct a one-tailed test with a 5% significance level to see if her claim is justified. This is a classic problem. Let's follow the 6 steps for a hypothesis test. Step 1. State the hypotheses. Let p be the probability of getting ahead. The null hypothesis is that the coin is fair, so p equals 0.5. The alternative hypothesis, based on Teresa's suspicion, is that the coin is biased towards heads, meaning p 0.5. Step 2. State the significance level, alpha, which is given as 0.05. Step 3. Identify the test statistic. The number of heads Teresa observed is our test statistic, which is x equals 15. Step 4. Calculate the p-value. Under the null hypothesis, our distribution is B20, 0.5. Since our alternative is p as 0.5, we are looking at the upper tail. We want to find the probability of observing 15 or more heads. Using a calculator, the p-value is px 15, which is approximately 0.0207. Step 5. Make a decision. Our p-value of 0.0207 is less than our significance level alpha of 0.05. This is the criterion for rejecting the null hypothesis. Step 6. Interpret the conclusion. Since we rejected the null hypothesis, we accept the alternative. We conclude that there is enough evidence at the 5% significance level to support the claim that the coin is biased towards heads. Teresa's suspicion is justified. Now let's look at another method for making a decision. The critical region approach. This method answers the question, how many successes would be too many or too few to be explained by chance under the null hypothesis? We define the critical region, C, as the set of outcomes where the p-value is less than or equal to alpha. Let's re-examine a previous example. Consider a four-sided die with the hypotheses H0, p equals 0.25, the die is fair for rolling a 1, against H1, p equals 0.25, it's biased towards rolling a 1. The hypotheses are H0, p equals 0.25, and H1p 0.25. The sample size is N6, and the significance level is A0.5. Our null distribution is B6.25. To find the critical region, we start with the most extreme value in the direction of the alternative hypothesis, which is 6, and calculate its p-value. For x equals 6, the p-value px6 is approximately 0.0244. This is much less than our alpha of 0.05, so x equals 6 is in the critical region. Now we check the next value, x5. PTX-EL5 is approximately 0.0464, which is also less than alpha, so x5 is in the critical region. Let's check x4. PX4 is approximately 0.0376, which is less than alpha, so x4 is also in the critical region. Finally, let's check x3. Px equals 3 is approximately 0.169, which is not less than alpha, so x53 is not in the critical region. This means that any outcome of 4, 5, or 6 would be considered strong evidence to reject the null hypothesis. This set is our critical region, C. The complement of the critical region is the acceptance region. A. In this case, if we observe 0, 1, 2, or 3 successes, we would not reject the null hypothesis. The critical value, C, is the value that defines the critical region. For an upper-tailed test, it's the smallest value in the critical region. So here, the critical value is 4. Now, let's say the die was rolled 6 times and 3 ones appeared. To make our decision, we compare the observed value x3 to our critical region. Since 3 is not in the critical region, we do not have sufficient evidence to reject the null hypothesis. We would conclude that the die is not biased towards rolling a 1. Now let's explore some IB-style practice questions related to hypothesis testing with the binomial distribution. We'll start with a one-tailed test. A car manufacturer claims that the brakes in 90% of their new cars last at least 50,000 kilometers. A government regulator suspects this claim is too high. She tests a random sample of 25 new cars and finds that 20 of them have brakes that last 50,000 kilometers. Is there enough evidence at a 5% significance level to support the regulator's suspicion? Let's break this down step by step. First, we define our variable. Let P be the true proportion of cars whose brakes last 50,000 kilometers. The null hypothesis, based on the manufacturer's claim, is P equals 0.90. The regulator suspects the proportion is lower, so our alternative hypothesis is P 0.90. We're given a significance level of 0.05. Next, we define our test statistic. The number of cars with lasting brakes is our variable x. Under the null hypothesis, x follows a binomial distribution with n unto 25 and p to 0.90. The observed value of our test statistic is x equals 20. Now we calculate the p-value. Since our alternative hypothesis is p 0.90, we are looking at the lower tail of the distribution. The p-value is the probability of observing 20 or fewer successes. Using a calculator, px equals 20 is approximately 0.468. We compare our p-value to alpha. Our p-value of 0.0468 is less than our alpha of 0.05. This means we reject the null hypothesis. Finally, the conclusion in context. There is sufficient evidence at the 5% significance level to support the regulator's claim that the proportion of cars with brakes lasting 50,000 kilos is less than 90%. Let's move on to a two-tailed test. Here, we're interested in any deviation from the null hypothesis, whether the true proportion is higher or lower. A recent study suggests that 65% of students who use an online learning platform achieve a passing grade in mathematics. A teacher suspects this is not the true proportion for their students and takes a random sample of 30 students. If 16 of them pass, is there evidence to support the teacher's suspicion at a 5% significance level? Let's follow our hypothesis testing framework. First, let P be the proportion of students passing. The null hypothesis, based on the study, is P equals 0.65. The teacher suspects this is not the true proportion, so the alternative is P is not equal to 0.65. The significance level is 0.05. Our test statistic is X, the number of students who pass. Under the null hypothesis, X follows a binomial distribution B 30 asati 0.65. The observed value is x equals 16. For a two-tailed test, the p-value calculation is slightly different. The p-value is double the probability of the observed outcome, or an even more extreme outcome, in the direction of the tail containing the observed outcome. Our observed value is x 16. The expected value under H0 is 30 times 0.65, which is 19.5. Since 16 is below the mean, we calculate the p-value using the lower tail. So we find px equals 16. Using a calculator, this is approximately 0.1364. Now we double this to get the two-tailed p-value, which is approximately 0.3528. Comparing this to our alpha, we see that the p-value of 0.3528 is much greater than our alpha of 0.05. Therefore, we do not reject the null hypothesis. The conclusion is that there is not enough evidence at the 5% significance level to support the teacher's suspicion that the passing rate for their students is different from 65%. A quick word about randomized tests. We have been using the binomial distribution, which is a discrete distribution. This means the p-value cannot be any value, it can only take a limited set of values. As a result, it's often impossible to construct a test that has a significance level of exactly 5%, or whatever our alpha is. For example, you might find that the p-value for a critical region of size 1 is 4%, and for a critical region of size 2 is 8%. You can't get exactly 5%. Randomized tests are a theoretical solution to this problem. The idea is that if you land on an outcome that is in this awkward middle ground, you flip a coin or roll a die to decide whether to reject the null hypothesis. The probability of rejection is carefully chosen to make the overall significance level exactly alpha. However, these tests are rarely used in practice, and they are typically beyond the scope of this course, but it's important to understand why they exist. They address a fundamental property of discrete distributions. This marks the 10-minute point of our video. If you're finding these concepts challenging, don't hesitate to seek expert help. DAR Tutors offers personalized online and home tuition in IB A-Level and IGCSE curricula. Contact us today to boost your understanding and grades. Once again, that's DAR Tutors. We're here to help you succeed. We now shift our focus to the second major topic, hypothesis tests for a population correlation coefficient. In Chapter 7, you learned about Pearson's product moment correlation coefficient, R. This R is a statistic, calculated from a sample of bivariate data that describes the strength and direction of a linear relationship. It's a measure for the sample. The true, unknown correlation coefficient for the entire population is represented by the Greek letter rho, R. It's pronounced RO. Our goal here is to use the sample correlation R to make inferences about the population correlation R. Our null hypothesis is always that there is no linear relationship in the population. In statistical terms, this means the population correlation coefficient is 0. So our null hypothesis is always H0 equals 0. The alternative hypothesis depends on what kind of correlation we are interested in. Just like before, there are three options. We can test for positive correlation, Pashar 0, negative correlation, Shashar 0, or any correlation at all, Chara 0. Notice these match the p-value calculation methods we just saw for the binomial distribution, upper tail, lower tail, and two tails. A key piece of theory for this topic is the bivariate normal distribution. This is a 3D probability distribution that arises when two variables, say x and y, are individually normally distributed and related to each other. We can visualize it as a hill. The height of the hill at any point, x, y, tells you the probability of those values occurring. The peak of the hill is at the means of x and y. The spread is controlled by their standard deviations. And most importantly for us, the shape of the hill is controlled by the correlation R. A strong correlation makes the hill stretched out, while no correlation makes it perfectly circular. The test statistic for this hypothesis test is a value t. This test statistic follows a t-distribution with n2 degrees of freedom. The formula for t involves r and n. While you don't need to memorize the formula, you do need to understand that the calculator handles it and that the resulting p-value comes from a t-distribution. Let's work through an example of a correlation hypothesis test using a graphics calculator. Consider the bivariate data set you see on the screen. We want to conduct a hypothesis test at the 5% significance level to determine if the variables are negatively correlated. The steps are very similar to the binomial case, but we use the calculator's built-in statistical test. First, we state our hypotheses. H0 is always Rosh equals 0. Our alternative hypothesis, H1, is Rory 0 because we are testing for negative correlation. Our significance level is A equals 0.05. Now the key step is using the calculator. First, input the X values into one list, e.g. L1, and the Y values into another list, e.g. L2. Once the data is entered, navigate to the Stat menu, then Tests, and select the lin-reg t-test or t-test for regression line. You will be prompted to specify your lists and your alternative hypothesis. For this test, make sure to select then select Calculate. The calculator will output a lot of information. The two values we care about are the test statistic, t, which is approximately 0.63, and the p-value, which is approximately 0.0706. Now for our decision. We compare our p-value to our alpha. Since the p-value of 0.0706 is greater than our alpha of 0.05, we do not reject the null hypothesis. The conclusion in context is that there is not enough evidence at the 5% significance level to conclude that there is a negative correlation between the two variables. We accept the null hypothesis that there is no linear correlation. Let's work through another IB-style question on correlation to reinforce the two-tailed test. The following table shows the scores of 10 students in a mathematics test and a physics test. We need to test for any association between the scores at a 1% significance level. The keyword association tells us we're looking for any linear relationship, positive or negative, which means this is a two-tailed test. Step 1. Hypotheses. H0, RO equals 0. H1, rho does not equal 0. The significance level is alpha equals 0.01. Step 2. Use the calculator. As before, enter the math marks into L1 and the physics marks into L2. Then navigate to the lin-reg t-test and select the alternative hypothesis rho does not equal 0. Calculate the results. The calculator will give you the test statistic t and the p-value. In this case, t is approximately 3.73 and the p-value is approximately 0.054. Step 3. Decision. We compare the p-value to alpha. Our p-value of 0.0054 is less than our alpha of 0.01. This is the condition for rejecting the null hypothesis. Step 4. Conclusion. Since we rejected the null hypothesis, we accept the alternative. There is sufficient evidence at the 1% significance level to conclude that there is a linear association between students' mathematics and physics marks. Let's conclude with a critical discussion about the limitations of hypothesis testing for the Pearson correlation coefficient. We can see here a scatter diagram of y against x. If we were to calculate the Pearson correlation coefficient r for this data, we would find that it is very close to 0, or even exactly 0. A correlation coefficient of 0 suggests there is no linear relationship between the variables. And if we ran a hypothesis test for r as Zasho, we would likely not reject the null hypothesis. But looking at the graph, it's clear there is a very strong relationship between x and y. It's not a linear relationship, but a quadratic one. The test for the Pearson correlation coefficient is only designed to detect linear relationships. It will not detect other types of relationships. This highlights a crucial limitation. The hypothesis test for Pearson's Yi can only tell you if a linear correlation exists. It cannot tell you if there is any relationship whatsoever between the variables. This is why you should always, as a first step, create a scatter diagram of your data. The scatter plot allows you to visually inspect the data for any patterns, including nonlinear ones, that a numerical test for Pearson's GR might miss. Let's quickly recap what we've covered today. We started with hypothesis testing for population proportions, using the binomial distribution for the p-value calculation. We then moved to hypothesis testing for the population correlation coefficient, which uses a t-distribution. We also briefly discussed randomized tests and, critically, the limitation of the Pearson correlation test for detecting only linear relationships. You are now equipped to tackle a wide range of IBAI-HL hypothesis testing problems. Remember the key steps for every test. State your hypotheses, define your significance level. Use your calculator to find the p-value or critical value and make your decision. Most importantly, interpret that decision in the original context of the problem. Practice is crucial for mastering this topic. If you need further assistance or want to work through more problems, remember that DAR Tutors provides expert, personalized tuition for IB A-Level and IGCSE students. Get in touch with us to boost your confidence and prepare for your exams. Thank you for watching.